Okay, I want to do exercise 1.37, parts 3 and 4. This is going to be very similar to how we did part 2. So I'm not going to go in as much detail as I did in those parts. Okay, so we want to know, let's say that we can solve the equation AU plus BV plus CW is equal to X. The question is it unique, or discuss when it is unique. So, something like that might have been a better wording. Okay, so let's assume it's not unique. So in other words, we can find other scalars, A prime, B prime, and C prime, not equal to A, B, and C, such that this is equal, such that this is true. Okay, well notice we can subtract the equations, and again, we get A minus A prime U plus B minus B prime V plus C minus C prime W is equal to the 0 vector. In other words, U is equal to B prime minus B over A minus A prime V plus C prime minus C over A minus A prime W. Okay, so in the previous example, if the solution was not unique, then we saw that U was a multiple of V. In other words, U was in the linear span of V. In this case, it's a little more subtle. U is not necessarily a multiple of V or W, but is in the linear span of V and W. So what this tells us is that anytime the solution is not unique, anytime the solution is not unique, one vector can be written as a linear combination of the others. In this particular case, since we're assuming A is not equal to A prime, B is not equal to B prime, and C is not equal to C prime, we actually can conclude that any of the vectors can be written as a linear combination of the other two vectors. Okay, so really what it means is that if you take a linear combination of V and W, or the linear span of V and W doesn't increase any when we add in the vector U. So the linear span of V and W is equal to the linear span of U, V, and W. So it's like U doesn't give any more information than you already got with V and W. Okay, now part 4 says answer the question. So really there's not enough information to answer that question. So if U can be written as linear combination of V and W, then yes, there are other scalars. If U cannot be written as a linear combination of V and W, then there are not other scalars, A prime, B prime, and B prime, all not equal to A, B, and C, such that A prime U plus B prime V plus C prime W is equal to X. Okay, so now let's look at number 4. Number 4 says, it's asking the same question, but in addition, we're assuming that there are scalars D not equal to 0, E not equal to 0, F not equal to 0, such that DU plus EV plus FW is equal to the 0 vector. Okay, so now, is there a non-unique solution? Well, think about it this way. AU plus BV plus CW plus DU plus EV plus FW is equal to X. Why is that? That's equal to X. That's equal to 0. X plus 0 is equal to X. So in other words, the linear combination A plus DU plus B plus EV plus C plus F W is equal to X. Now we'll say A prime is equal to A plus D, B prime is equal to B plus E, and C prime is equal to C plus F. Since D, E, and F are none of them are equal to 0, it means A prime is not A, B prime is not B, and C prime is not C. Okay, so now think about what I'm about to say. Whether or not the equation AU plus BV plus CW equals X has unique solutions, whether or not that has a unique solution, depends on whether or not you can write U as a linear combination of U, V, and W, where the weights on the linear combination are not equal to 0. Okay, so we can always, for any three vectors u, v, and w, we can always write 0 as a linear combination of u, v, and w just by taking the weights d, e, and f all equal to 0. Okay, but what we have seen in these two examples is that we can write, is that the solution to the equation au plus bv plus cw equals x, the uniqueness of that solution depends only on whether or not we can write 0 as a unique combination of u, v, and w. If we can write 0 as a unique combination of u, v, and w, there's only one solution, or there's at most one solution to the equation au plus bv plus cw is equal to x. Okay? If we can write 0 as a non-unique linear combination of u, v, and w, then there is a non-unique solution. If there is a solution, there's a non-unique solution to au plus bv plus cw is equal to x. Okay, think about what I said. This is important. It's related to a concept called linear independence that we will get to in chapter 2, but we're going to talk about it now. You don't need to know the terms to answer questions like these.